Alright, now that we know the basics of reversible reactions, let's try to understand the Haber process. Now, Haber process is simply the reaction between nitrogen gas and hydrogen gas to produce ammonia gas. One volume of nitrogen reacts with 3 volumes of hydrogen to produce 2 volumes of ammonia gas. Alright, the forward reaction, which is represented by this arrow, this upward arrow, it is when nitrogen reacts with hydrogen to give off ammonia. The reactants in this case are nitrogen and hydrogen gas, and the products in this case is ammonia gas. And the backward reaction, which is represented by this left hand side arrow, and over here, which goes towards the left side. Alright, now this is the backward reaction. It has reactants which are ammonia gas, and notice that these reactants were the products in the forward reaction. Alright, reactants in the backward reaction were the products in the forward reaction. And ammonia gas, it again decomposes into nitrogen gas and hydrogen gas, and these products on in the backward reaction, these were the reactants in the forward reaction. Alright, so this is basically the equation for the Haber process, equation for the manufacturing of ammonia gas. Now, basically what was happening is nitrogen and hydrogen are reacting together to form ammonia gas, and ammonia is then decomposing back to nitrogen and hydrogen gas. Because this is a reversible reaction, both these reactions are taking place at the same time. Nitrogen and hydrogen are being converted into ammonia, and ammonia is continuously being decomposed into nitrogen and hydrogen gas. Alright, both these reactions are taking place simultaneously at the same time. Now what happens is there comes a point where the rate of forward reaction equals the rate of backward reaction, which means that the amount of ammonia that is being produced is equal to the amount of ammonia that is being decomposed. Alright, so which means that there is a dynamic equilibrium that is reached. Dynamic equilibrium is the point at which the rate of forward reaction equals the rate of backward reaction. At this point, the percentage yield is 0. Alright, we do not obtain any net ammonia. And when we talk about the yield, we always focus the forward reaction. Alright, so at the dynamic equilibrium, the amount of ammonia that is being produced is equal to the amount of nitrogen and hydrogen gases that are being produced, that are being converted back from ammonia. Alright, the percentage yield of 10% means that the volumes of nitrogen and hydrogen that are reacting together to produce ammonia, only 10% of ammonia is being produced. For example, if there are 100 volumes of nitrogen and hydrogen, and ideally it should 100 volumes of if 100 volumes of ammonia should be produced, if this reaction was only the forward reaction, then 10% yield means that only 10% of the volume that should be produced is actually being produced. Alright, and the yield percentage yield of 50% means that the amount of ammonia, for example, if the amount of ammonia that must be produced theoretically in forward reaction is, let's say, 50 or let's say 30 decimeter cube, 50% yield means that only 15 decimeter cube of ammonia is being produced. The rest 15 decimeter cube is again being converted into nitrogen and hydrogen gases. Alright, this is because of the reversibility of this reaction. Now, there are certain conditions, there is a set of conditions that was given or that was proposed by Haber, which make this production of ammonia the most efficient and which give us the maximum possible yield of this ammonia gas during the Haber process. And what are these conditions? Obviously, the raw materials are nitrogen and hydrogen. Nitrogen is obtained from fractional distillation of air, and hydrogen is obtained from cracking of crude oil. And the conditions are a high pressure of 250 atmospheres is used, alright, and a high temperature of 450 degrees Celsius is used. And the third condition is a finely divided iron catalyst. Iron is used as a catalyst, and it is a finely divided, a small powdered form iron that we use during the Haber process. Now we use a very high temperature and pressure because the nitrogen gas is unreactive at room temperature. Alright, so it won't have any reaction with hydrogen if we use normal room temperature and pressure conditions. That is why we use a high pressure and a high temperature to make nitrogen reactive. Alright, now what happens, why do we use this amount of pressure and this temperature? Why do we use 250 atmospheres and why do we use 450 degrees Celsius? Let's have a look into it. If you see over here that if you look at the temperatures, then you'll notice that increasing the temperature, it actually decreases the yield of ammonia gas. Alright, which means that if at lower temperature the yield will be low. If the temperature is low, the yield of ammonia will be higher. Alright, so lowering the temperature increases the yield of ammonia and reduces the decomposition of ammonia to nitrogen and hydrogen, which means that if we decrease the temperature, then the forward reaction increases. Forward reaction is the favorable reaction that we want. Alright, and if we reduce the pressure, alright, if we lower the pressure, then the rate of reaction it also reduces, which means that pressure increases, then the yield increases. When we reduce the pressure, the yield will also be reduced. There is an indirect relation between temperature and yield, but there is a direct relation between temperature and yield, which means that we need to have a lower temperature for maximum yield and we need to have a high pressure for the maximum yield. Alright, why is the low, but there are a few problems when we reduce the temperature. Why? Because lowering the temperature, we have seen that the nitrogen becomes unreactive when the temperature is reduced. So lowering the temperature will reduce the rate of reaction. Rate of reaction is decreased. Rate of reaction decreases when we lower the temperature. Alright, but when we increase the pressure, uh, further, when we do it more than 250 atmospheres, then there are again certain conditions that we need to apply. For example, we need to have special pumps if we need to increase the pressure even more, right, for even more yield. And we also need to have stronger pipes so that they can withstand the increased amount of pressure. Alright, yield of ammonia is increased under high pressure. The rate of reaction is also increased. We have studied that in the previous chapter. that increasing the temperature increases the of rate of reaction, but it decreases the yield of ammonia, or it will also increase the rate of the backward reaction. That is why the yield of ammonia will be less. Now there is a difference between yield and the rate of reaction. Yield of ammonia means that how much of the ammonia is being produced, what percentage of reactants is being converted into ammonia. Yield shows the rate, the forward reaction, how much forward reaction is taking place. All right, here we discuss that yield of 50% means that out of 30 decimeter cube, 15 decimeter cube of ammonia is being produced. Rest 15 is again being converted into nitrogen and hydrogen gas, whereas the rate of reaction means that what is the speed of the reaction, how quickly are the reactants being converted into products. Alright, so we've discussed the effect of temperature and we've discussed the effect of pressure. Now let's talk about catalyst. Now catalyst, we know that it increases the rate of reaction, or it has no effect on the yield. The yield of ammonia will remain the same by adding the catalyst, and the catalyst is the finely divided iron catalyst that we've seen. But the catalyst will increase the rate of reaction. Alright, even after applying high temperature and pressure, the reaction is slow. So that is why we need to add catalyst so that the rate of reaction, the speed of reaction can be further increased. Let's quickly summarize this. Temperature's effect is that we increase the temperature, alright, 450, 500, 600, the yield is low. Obviously the rate will be higher, but the yield is low. So that is why we want the maximum yield of ammonia. We want the maximum reactants to be converted into products. So that is why we use a lower temperature. But what happens when we use a lower temperature? The rate of reaction decreases. Alright, so we need to find a compromise between the rate and the yield. Similarly, when we increase the pressure, the yield of ammonia is higher. For example, you can see it is 100 over here, and at 100 atmospheres it is over here, and at 400 atmospheres the yield is higher, and at 100 atmospheres the yield is over here, and at 400 atmospheres the yield is around 40. At 100 it was around 20, and at 450 degrees Celsius the yield at 100 was around 30, and the yield at 400 atmospheres was at about 50%. Alright, so the yield increases when we increase the pressure, but again when we increase the pressure we need to have special pipes, we need to have stronger pipes and special pumps which can withstand higher which can withstand higher pressures. Now which means an increased cost. So increasing the pressure will increase the yield, but the cost of production will be higher. So again we need to find a compromise between the cost and the yield to decide about the pressure. And whereas the catalyst, it will only increase the rate of chemical reaction, the rate of forward reaction. Alright, the catalyst will not have any effect on the yield. It will only increase the speed of reaction. I'll see you next time. I hope it makes sense.